Hello everyone. Today our topic is subdomain collocation method. These images that you see here have got no relevance with subdomain collocation method. They are not pertinent to subdomain collocation method. But I have put these images just to emphasize one point. The concepts and the tools that you learn in finite element analysis. It is a mathematical subject. It is not going to stay in your brain unless or otherwise you review and revisit the concepts again and again and again. So I highly recommend that you put a separate notebook for finite element analysis and also cover the notebook with white cover. I pulled this trick from Steve Jobs. Steve Jobs used to paint everything around his room white in color. The reason is because if there is a picture on the wall, then that picture also acts as a distraction. So don't record anything irrelevant in the notebook, and also make sure that this notebook is like a diary that should travel with you throughout your life, particularly if you are going to become a design engineer. Also, Sachin Tendulkar, he would not give his clothes to laundry, particularly his uniforms. He used to iron his own clothes. As he irons his clothes, he used to mentally rehearse what are the shots that he used to play. Therefore, you mentally rehearse before you go to sleep. Whatever concepts that you learn, you please mentally rehearse. And this player, legendary player, Andre Agassi, he would not allow anyone to touch his tennis bag. The reason is because if anyone touches his tennis bag and if there is a mess in the tennis bag, then that affects the way he plays his shots. Therefore, I highly recommend that you keep your table, you set your table in order. Because if your table is in order, if your table is neatly packed, then that forms a conducive learning environment. Now let us delve deeper into subdomain collocation method. So subdomain collocation method is superior to point collocation method. If you ask me this question, in what way subdomain collocation method is superior to point collocation method? Subdomain collocation method tries to make the residual zero in an overall sense. So in that way, subdomain collocation method is superior to point collocation method. It tries to make the residual is analogous to error. It is not synonymous with error, but the word residual is analogous to error. So subdomain collocation method tries to make the residual zero in an overall sense. In that way, it is superior to point collocation method. So as the class progresses, we will see the physical meaning of subdomain collocation method. We will see the tangible meaning of subdomain collocation method, something that you will really be able to appreciate. Okay, now we are going to solve the problem of a simply supported beam subjected to uniformly distributed load by subdomain collocation method. So I'm drawing a simply supported beam. Let me define the geometric properties of this simply supported beam. The simply supported beam has got a length of magnitude L. It has got moment of inertia, that is I. Remember, moment of inertia is resistance to bending. Greater the moment of inertia, greater the resistance to bending. This beam is made up of material that has got an Young's modulus of magnitude capital E. So what is the stuff that is acting on this beam? This beam is subjected to uniformly distributed transverse load. So let me say that the rate of loading is Q. Its unit can be Newton per meter or it can be Newton per mm. So it is subjected to uniformly distributed transverse load. So what is the governing differential equation? So let me write the governing differential equation of a beam that is subjected to uniformly distributed transverse load. It is EI into d power 4 V by dx power 4 minus Q is equal to 0. In some textbooks, they put Q naught. Okay, we are fine with Q. EI d power 4 V by dx power 4 minus Q is equal to 0. So that is the governing differential equation. Let me write the boundary conditions. Boundary conditions are the value of deflection at x is equal to 0 is 0, deflection here. And the value of deflection at the right extreme end is 0. So V of L is equal to 0. The bending moment which is ei into d square v by dx square at x is equal to 0 is equal to 0. The expression for bending moment is ei into d squared v by dx squared. You have to burn this expression into your brain, and I have explained how we exactly arrive at this particular expression for bending moment in the derivation for governing differential equation of a beam. Okay, and the bending moment at the right extreme end, that is bending moment at the right extreme end, that is also going to be 0. So it is ei into d square v over dx square at the right extreme end, that is at x is equal to L is equal to 0. So that's the boundary conditions. These are the boundary conditions. So I'm going to do the first step. The first step to solve this governing differential equation, it is to assume a trial solution. So here we go. Let me assume a trial solution. So the very first step is to assume a trial solution. And we know what is the trial solution that we have to assume. The trial solution that we have to assume is a trigonometric trial solution, that is v of x is equal to a into sine pi x over L. So this is the trial solution that we have to assume. The reason for assuming this particular trial solution is obvious. It is quite axiomatic that the beam actually bends in a sinusoidal fashion. So that is one of the reasons why you have to assume this particular trial solution. The second reason is that this trial solution satisfies all these boundary conditions. So if you put x is equal to 0, v becomes 0. If you put x is equal to L, v becomes 0. The bending moment, which is ei into d squared v by dx squared, if you just turn the crank of mathematics, and if you find the value of ei into d squared v by dx squared and substitute at x is equal to 0, you're going to get 0. Substitute ei d squared v by dx squared at x is equal to L, you're going to get 0. So that is the reason why you have to assume this particular trial solution. So it is so appealing. Okay, the second step, we know that it is satisfying the boundary condition. Okay, the next step. So second step is we found that the boundary conditions BC, boundary, I'm sorry about this terrible C. Let me erase that. Here we go. Okay. Okay, the boundary conditions are satisfied. So that is step number 2. And let me do the third step. The third step is to find the value of d power 4v by dx power 4. So let me write. So find d power 4v by dx power 4. And if you find d power 4v by dx power 4, which I'm going to do straight away, you see, if you differentiate this particular trial solution 4 times, one time differentiation is going to give you cos pi x over L into pi by L. So 2 times differentiation is going to give you minus sine pi x over L into pi by L. Already there is a pi by L. There is going to be a pi square over L square that is being factored out of that equation. So let me write the 4 times differentiation of that equation. It is a into pi raised to the power 4 over L raised to the power 4 into sine pi x over L. Check the mathematics. So it is going to be, if you differentiate the trial solution 4 times, if you find d power 4 v over dx power 4, it is a pi raised to the power 4 over L to the power 4 into sine pi x over L. That's what I have written. So that is step number 3. We are clear with step number 3. So I will put a tick mark for step number 3. So what is going to be step number 4? Step number 4 is you have to substitute the value of d power 4 v by dx power 4 in the governing differential equation. So just go ahead and substitute the value of d power 4 v by dx power 4 in the governing differential equation. So here we go. In the governing differential equations, you have to substitute the value of d power 4 v by dx power 4. I'm indicating that by this blue here. So let us substitute and let us turn the crank of mathematics. Let us see what mathematics has got. So if you substitute the value of d power 4 v by dx power 4, what you are going to get is ei into a into pi raised to the power 4 over L to the power 4 into sine pi x over L. So this is d power ei into d power 4v by dx power 4. So this is d power 4v over dx power 4 minus q is equal to, we should not be saying 0. I have explained that reason in point collocation method, because if you are putting 0, you are going to find the value of the constant in terms of a variable, which is a mathematical violation, which is analogous to error. So there is a residual error there that kicks around. So you call it as residual, denoted by the symbol capital R. So in this process, you are computing the residual, the equation for residual, right? You are computing the equation for residual. You see that this residual, which is analogous to error, is a function of x. It is clearly a function of x, which means that you can plot a graph by taking the residual along the y-axis and x along the x-axis. You can plot a graph. So in the point collocation method, we actually plotted the graph. And suppose if you're going to get a graph that looks something like this, by taking the residual along the y-axis and x along the, which is the location, normalized location, axial location of the beam along the x-axis. So if you are going to get a curve something like this, right, you can find the area of the curve. What is the physical meaning of residual? I think we have already seen the physical meaning of residual. If you work out the unit on the left hand side, the unit is going to be Newton per meter, which means that residual is something which is error. It has a unit Newton per meter. What has the unit Newton per meter? Well, it is the rate of loading. Here we go. It is the rate of loading. So we can safely say that residual is error in rate of loading. So there is an unwanted load, rate of loading that is kicking around. So that is the physical meaning of residual as far as this particular problem is concerned. Okay, now if you can plot a graph something like this by taking the residual along the y-axis and axial location of the beam along the x-axis, you can find the area of this curve. So how do you find the area of this particular small strip? Well, what is the height of the small strip? It is capital R. What is the length of the small strip? It is dx. So R into dx gives the small area. So if you want to find the total area of the total area just beneath this residual curve, all you have to do is you have to integrate over the limit 0 to L. Let us say that it varies from 0 to L. Now, why do you want to integrate? So that you can find the area beneath the curve. And if you can force the condition, what you are actually doing is you are forcing a condition that the area should become 0, which means that you are sort of trying to flatten this curve. So that is what you are trying to do. You are trying to flatten this curve. You are trying to reduce the error in an overall sense. So that is the physical meaning of subdomain collocation method. You are trying to flatten the residual. So in other words, capital R has the term A, which means A sine pi x by L. A is a constant that you have to find out. What you are actually doing in this particular equation is, you are actually, listen to my words very carefully, and please, after listening, burn this particular phrase into your brain. What you are actually doing in subdomain collocation method is, you are actually asking a question. That question is, what is the value of A? What is this particular value of A? Which, when substituted in the trial solution, makes the area beneath the residual curve 0. So allow some time, give some time for the concept to sink in. So I will repeat this phrase again. What is the value of A? Which, when you substitute in the trial solution, makes the area beneath the error 0. Remember, it is not making the error 0. It is just making the area beneath the error curve, residual curve, 0. So that is the physical meaning of subdomain collocation method. So you may ask me this question: if you are making the area 0, which means that error should vanish, but that is actually not the case. Let me explain the reason why. If you are making the error 0, if you are making the area of the error curve 0, there is a possibility for negative loop as well as positive loop. So this is negative, and this is positive. So this positive, which is indicated by this green here, and this negative, which I will indicate by this yellow here, if you sum them, the area may cancel out and the total area may become 0. That doesn't mean that error is 0, because error exists. Error exists here. Error exists here. So you see that subdomain collocation method is not the superior method. Maybe it is superior to point collocation method, but it is not a superior method, because in subdomain collocation method, still the error actually kicks around. So that is, so you are actually trying to make the error 0 in an overall sense in subdomain collocation method, but still the error is there. So that is subdomain collocation method. That is the physical meaning of subdomain collocation method. So I will apply the subdomain collocation method to this particular problem. So we know the equation. It is integral of r into dx is equal to 0 over the limit 0 to L. So in the next step, it is integral over the limit 0 to L. What is the value of r? It is ei. Here we go. I will just tell you what is the value of r. Here we go. It is ei a pi raised to the power 4 over L to the power 4 sine pi x over L. So that is the value of r. So it is ei into a into pi raised to the power 4 over L raised to the power 4 into sine pi x over L minus q, that is r, into dx is equal to 0. So what I'm going to do is I'm going to take a constants outside and I'm going to integrate the sine pi x over L. So with respect to x, so it is ei. So I will take this a, put it on the first, a into ei into pi raised to the power 4 over L raised to the power 4. And if you integrate sine pi x over L, what you're going to get is minus cos pi x over L divided by pi by L. So what I will do is, it is minus cos pi x over L whole divided by pi over L over the limit 0 to L. And if you integrate this q here, what you are going to get is, you will be getting q x over the limit 0 to L. In the next step, I'm going to take this minus sign outside, so I'm kind of retracting the minus sign outside. It is minus a into ei into pi raised to the power 4 over L raised to the power 4 and into L over pi. If you take this pi by L to the numerator, it is L over pi. And if you substitute the upper limit in this equation, I have already taken this minus sign outside. If you substitute the upper limit, which is capital L, you get cos 180 degree, which is minus 1. Minus of, if you substitute the lower limit, cos 0 degree, it is 1. So it is, you're going to get this. Minus, if you substitute the upper limit, you will be getting q over L. And that is equal to 0. So let me do the next step. Let us proceed. So what you are going to get is, it is minus 2 here. So it is minus 2 into minus, you are going to get plus 2. So it is 2a ei pi raised to the power 4 divided by L to the power 4. So it is 2a ei pi raised to the power 4, but already there is a pi in the denominator and already there is an L in the numerator. So what you are going to get is, it is pi cube over L cube. That is nice. And you take this QL onto the right hand side, so you are going to get is equal to QL. So all you have to do is find the value of A. So it is QL raised to the power 4 over 2ei into pi cube. So that is the value of A. I have got the value of A. So this is the value of A, which when you substitute in the trial solution makes the error area, which is the residual area, 0. Remember, it is only making the area beneath the curve 0. It is not making the error 0. So of course, subdomain collocation method is superior to point collocation method, but there are other methods available that are superior to subdomain collocation method. Okay. In the next step, I'm going to substitute the value of v of x is equal to a sine pi x over l. So that is the equation. So v of x is equal to, if you substitute the value of a, it is q l raised to the power 4 over 2 ei pi q. Pi q into sine pi x over l. So that is the solution to this problem. I invite you to substitute, assume a value for q, which is rate of loading. And if you know the geometric properties, definitely you should know what is the length of the beam, what is the moment of inertia of the beam. And if you know what is the material with which the beam is made of, suppose the beam is made of concrete or whatever it is, steel, you also know the Young's modulus value. You know the number 2. And you can feed all the values and you can plot the value of deflection, which can be taken along the y-axis. And you can take at different positions on the beam, you can plot your graph. And you can compare it with the exact solution. I invite you to do this particular exercise. Maybe you can use Excel or you can use MATLAB by taking the deflection along the y-axis and taking the location of the beam along the x-axis, and you can plot your graph and you can find out that subdomain collocation method is actually superior to point collocation method. In the next class, we will see a method that is superior to subdomain collocation method, which actually gave birth to finite element analysis. In the next class, we are going to see Galerkin's weighted residual method. Thank you all for your patience. Radiate hope and do amazing work. Thank you.